Everyone. Today I'm going to talk about a very important phenomenon in material science called thermal creep, also known as thermofluency or simple creep. For this, my team is conformed by William Rodriguez, Mango my cat, and Johnny Jimenez, and myself, obviously, Hector Peña. Okay, what's thermofluency? Thermal creep is a slow and progressive deformation of a material when it's subject to a constant at load at high temperature. Okay, for a long time period, in simple words, even if this force applied to a material does not change. The material keeps deforming little by little without break. Mm, so that will become deforming past time, and the heat is the same. At high temperatures, the inside the material, the atoms starts to vibrate and move more easily. This makes it possible for the internal layers to slide over each and other, and the microscope movement causes the material to slowly change a shape. A shape. Okay, a simple example. Imagine a metal bar holding a weight inside a furnace. The weight starts the same, but several hours the bar becomes longer and thickly bent. It doesn't breaks right away. It just deforming slowly, time by time. That's thermal creep. Okay. So what's the cause? There are three main factors that make that thermal creep happen. Okay, one is high temperature that gives the energy necessary for the atoms to allowing their move more and more easily. Okay. Second is the constant load. Even if the force doesn't change, it a continuous stretch weakness to the atomic bonds. How that mean? Long exposure times. Okay, long exposure times make the creep occurs over an hours, days, or even years. Because this not occur instantly. Because of that, engineers study creep when designing materials that must the long time under a heat and stress that the creep doesn't happen.
Okay, alright. I'm going to talk about the creep deformations. I will talk about the stage of creep. Creep deformation usually happens in three stages. The primary stage, deformation starts quickly, but the rate soon slow down as the material adjusts to the load. The secondary or steady stage, the deformation continued at a constant rate for most of the material's lifetime. This is the most stable and the longest stage. And finally, the tertiary stage, finally the deformation rate increases again until cracks appear and the material fails. If we graph deformation versus time, we can clearly see these three stages forming a smooth curve. And a technical exam, a clear example of thermal creeps appears in aircraft engines. The turbine's blade operate at extremely high temperatures, something about 1000 degrees Celsius. If the material blades deformed due to creep, the engine could lose balance or even break apart. To prevent that, engines use superalloys made from nickel, titanium, and other materials. The real life applications is thermal creep isn't something we use, but rather something we must consider and controls in engineers designs. Here are some case applications.
Okay, so some real life applications are on aviation and turbines. Engineers calculate how much a part will deform over time and choose materials that can resist a creep at high temperatures. This guarantees safety and performance on jet engines and powerful turbines. Second is the application on power plants and nuclear reactor. Pipes or valves are exposed to constant heat and exposure, so creep can make them stretch, bend, or crack, causing dangerous leaks. So engineers perform creep life applications to predict how much and how long components will last before replacement. The third is the automobile engines. Inside cars engines are pistons and valves that face very high temperatures. If they deform due to creep, they can drop efficiency. That's why they are made from heat-resistant alloys that maintain their shape even after thousands of hours of use. The fourth use is on construction and metal structures. Bridges, towers, buildings are exposed to long periods of heat due to sunlight, and these may suffer creep deformation over the years. Structural engineers include creep coefficients in their design calculations to ensure long-term safety. And fifth is plastic and electronic components. Some polymers deform easily with heat in electronic devices that could cause loose connections or short-circuits. For that reason, high-temperature polymers are like PTFE or PEEK are used to keep their shape even under conscious heat.
And how it is studied in laboratories, engineers perform creep tests by placing a material sample under a constant load and maintaining it at a specific temperature. They measure the deformation over time and draw a creep curve. From the data, they can predict the expected lifetime of the material in real conditions.
Thermal creep is essential in the material science because it helps engineers predict how the materials behave over time. By understanding it, we can design safer and more durable machines, engines, and structures. Ignoring creep could cause serving failures, and if the load never increases, only because of temperatures and time.
Okay. Okay, guys. Now I will talk about factors that influence creep behavior. That way, a material deforms to creep depends of several case variables. The temperature is the most important one, as increased atoms gain energy and move more easily, so creep rate rise exponentially. So the upward stress is also essential. Even a small increase in load can make the material deform much faster. So another factor is the microstructure of the material. Factors like grain size, the location, and phase composition determines how resistant is an atomic movement. So the metals with a larger gains, for example, tend to resist a creep better because they favor gain boundaries, where atoms can move. So that's why the high performance application engineers carefully control the manufacturing process to optimize these microscopic factors. That's so important because if the engineers choose the material bad, that will become in a a big mistake, and maybe an death. At the atomic level, there are different mechanisms that explain how creeps happens. First, in the location creeps, the atoms move along the crystal defects, allowing large atoms slip gradually. In the fusion creeps, okay, atoms migrate into of the lattice along the gain bondage. So there's also a gain bondage sliding, where intergrains shifty and slidey relative to each other. Uh, each of these mechanics dominates depend of the temperature and the uplift stress. Why student groups matter? Understanding which mechanism domains allow engineers to predict how materials will behave in the real environments. So, for example, turbine blades, pressure, wheel cells, engine parts are designed not only for strength, so they have by combining in laboratory data with a computer simulations, so that they need a creep resistance because that can't be fail in any moment. So that will be a huge mistake that I say after. By combining laboratory data with computer simulations, scientists can estimate how long a material will last before a significant deformation occurs. Sometimes predicting lifetimes at tens of thousand hours. Okay, to sum up, thermal creep is a slow and permanent deformation that occurs all the time with all the materials, but one materials is more slow and another is more fast. That depends on degrees and the material. Okay. Also, This happens when a material is exposed to a constant stress and a high temperature for a long period. This may seem like a small effect, but it's a huge impact for our safety or of the safety of all the workers that work in on airplanes and machines. Okay, so thanks to study of the creep, we can build airplanes that can fly safely and power plants that have a decades of functionament. So under extreme conditions, understanding thermal creep means understanding how time, heat, and matter interact to in the real world. Okay, thank you everyone.
Now, a small example of the cryptid will be this. Basically, I have a wire to which I will apply heat. At its base, the wire has a weight, and as it heats up and turns red, I will it will slow, begin to elongate in its plastic region until it reaches a breaking point at throw. More heat will be needed for that. However, with the amount of heat I apply, it will be enough to notice a side of stretch of the wire, and that will be with the whole experiment. Now we can see how the wire is turning red and stretch a little bit.
Okay, for our game, we have a game that is competition to put as many clips as possible on this string, like this. It will be a game for two. So the setup is you put wait you put the straw right here, and you put first this clip that is gonna be the base of everything. You put it right here on the left side and the right side, and then you put the fire right there. The objective is to put as many clips as possible on the other clip until the straw bends because of the weight and falls over. You see right there, the straw is starting to bend because of the weight. Then I put it right here. It will work even more fast if the clip is near to the fire, because again of the weight, and slowly will bend over and fall.
Thank you everyone. This will so hard.